All right. We are live again. Late stream tonight. I have to admit these are kind of hard to fit in because it's very taxing to do these. But anyways, we're back at it. We got 2 different chapters today. We're gonna try to get through these as quick as we can. Today we're doing chapters 12 and 13, which I just completely messed up. Let's see here, 12. So 12 and oh, there you go. Audio checks are good. Oh, I said that wrong actually. Today we're doing chapters 17 and 18. Chapter 17 is Vocabularies, Terminologies, and Nomenclatures, and chapter 18 is Data, Taxonomies, and Ontologies. Should be a pretty fun chapter. I think I'm going to keep it pretty brief since this is just foundational knowledge, so maybe just some short definitions of this, and we might actually even end sooner than an hour. So let's go ahead and get started. Always starting off with a nice Google search. Look at this. There's someone that has like cards here. This is pretty nice. Let's see what these cards that they used were. So a clinical vocabulary terminology that lists words or phrases with their meanings, provides for the proper use of clinical words as names or symbols, and facilitates mapping standardized terms to broader classifications for administrative, regulatory oversight, and fiscal requirements. Classifications. There's a couple terminology standards. What is this? Nurse key? Let's find a decent article here. Ooh, Chris Shute. Chris Shute is always a great guy. This is from about 2000. Clinical classification. So there's terminology, and there's vocabulary, and then there is, what's the last term we're looking for? Nomenclature. Yeah, let's go ahead and read this article. Maybe cite this. Chris Shute is a very well-renowned guy in informatics, so we're gonna cite his stuff. Let's go ahead and some history and current observations. It's a little outdated with 2000. Maybe we're bringing another one. Let's just see what this one shows, and then we'll come back to this. Cite this. Classifications. Right. Copy paste. I really wish this was a little faster. The lag was Zotero was a little annoying. Okay, so I think we're good here. Let's go ahead and read through the article. Clinical classifications. The evolution of health terminology has undergone glacial transition over time, although this pace has quickened recently. After a long history of neglect, unimaginative structure, and fictitious development, health terminologies are in an era of unprecedented importance, sophistication, and collaboration. Major highlights of this history are reviewed together with important intellectual advances in health terminology development. The inescapable conclusion is that we have missed a major revolution in the role and capabilities of terminologies, entering an age of large-scale systems for health concept representation with international implications. It is easier to speak about health terminology than to write about it, since people may read and wonder exactly what is meant by this word or that term. The meta-terminology of terminology is no exception, fraught as it is with notions of concepts, classifications, nomenclature, and terminology. The reality is these words are often used casually, imprecisely, and even interchangeably. I'm probably guilty of that. Formal distinctions do, of course, exist and warrant some overview. The abstractions implicit in a concept date at least to Plato's articulation of a perfect form, apart from the shadow of that form in this world. Plato classified things by using strict divisions, a method rejected by Aristotle, who replaced dichotomy with the syllogism or logical premise. Aristotle made this more practical, yet introducing the notion of differentia, which could serve to distinguish or describe form. Indeed, one can almost deduce that the entire genre of multi-axial classifications were anticipated by Aristotle, if one replaces the modern notion of classification axes with attributes about specific differences. Put simply, Aristotle introduced the notion that abstract concepts represent descriptions, or more properly, definitions of things that have been classified by describing their attributes. But abstract descriptions are not words or terms. Strictly, nomenclature simply means the naming of things. However, to name something implies knowledge of its form. Perilously close to an Aristotelian definition, conventionally, however, nomenclatures can be nothing more than lists of recognized or sanctioned words and have little or no relationship to a system of classification. Indeed, some dreary examples illustrate just how removed from useful organizing schemas some nomenclatures can be. However, classifications and nomenclatures can be more helpfully regarded as lying along a continuum where the first categorizes and aggregates, while the second supports detailed descriptions. Finally, terminology invokes the language labels attached to a concept. Here one can become horribly distracted by eponyms or word origins, tracing the Greek, Latin, or even Norman routes of our English language. However, this view is profoundly ethnocentric, since the language labels used for medical concept by speakers of different languages may well be quite different, rendering the study of which term to use essentially a local concern. This may be usefully be distinguished from the concept systemization to which a language labeled term might be attached, hardly a local concern if comparability, consistency, and interoperability are shared goals. Terminology, then, is a convenient moniker, which can mean everything or very little. Many authors, including I, invoke terminology to subsume the entire problem, from classification to nomenclatures, language labels to concepts. Practically, we mean the naming problem, enabling clinical users to invoke a set of controlled terms that correspond to formal concepts organized by a classification schema. I can't say this is something that I probably want to read through right now. I think I want to find something that's a little bit more recent. This is great for like a history lesson, but maybe not. So I think I'll find something else. Probably not going to really test you on that, and you probably it's just like don't really need to know that kind of stuff. So let's go ahead and look for something else. What is this one? HHS.gov. National Committee on Vital. So this is good. Health terminologies and vocabularies. So vocabularies, terminologies. Studies the adoption. Blah, blah, blah. It says health terminologies. Take a look at. Let's see if they have any definitions that we can use here. Here we go. We'll use this. This is perfect. Okay. It's just understanding the exact definitions, I think, is always really important to know. So I'm going to cite this. And this is, what's this? Health terminologies and vocabularies. Presentation by HHS. What's this one? Move this over here. This is National Vital Health Statistics. So let's go ahead and cite. I don't know if I cited it. Vocabulary. Health terminologies. No. National Committee. NCVHS. for now. Let's go back to the definitions. Okay, here we go. Just send the link. Let's go terminology, code, classification, vocabulary, nomenclature. Okay, so where is this from? As required by administrative. Defined. Uniform data standards for the patient medical record information as required by administrative of HIPAA. Okay, this looks fine. A collective term used to describe the continuum. Terminology. Collective term used to describe the continuum of code set, classification, and vocabulary. A representation assigned to a term so that it may be more readily processed. In general, most terminologies incorporate a coding system for computer processing. I don't think I've ever read through the formal definitions of these. Classification is arranges or organizes like or related terms for easy retrieval. Like or related terms. So it's like groupings, if you will, right? Arranges or organizes like or related terms for easy retrieval. An example is like ICD-10. Vocabulary, a set of specialized terms that facilitates precise communication by minimizing or eliminating ambiguity, e.g. SNOMED, CT. A set of specialized terms that facilitates precise communication by minimizing or eliminating ambiguity. So there's controlled vocabulary, which indicates only the set of individuals or individual terms in the vocabulary, indicates only the set of controlled, and there's structured vocabulary, which is or reference terminology, relates terms to one another with a set of relationships and qualifies them with a set of attributes to promote precise and accurate interpretation. These relationships and attributes may be represented in some type of an information model. Vocabularies are mapped to standard terminologies. Nomenclature, synonym of vocabulary. Let's try to understand this a little more. One more time. Terminology, a collective term used to describe the continuum of code set, classification, vocabulary. Code makes sense, just some code for processing. Classification is like grouping. How do you arrange or organize like or related terms for easy retrieval? Vocabulary, set of specialized terms that facilitates precise communication. So it should be using vocabulary, so clinical vocabulary. Okay, so these are like almost like your standards. Controlled vocabulary indicates only the set of individual terms in the vocabulary. Structured vocabulary or reference terminology relates terms to one another with a set of relationships and qualifies them with a set of attributes to promote precise and accurate interpretation. These relationships and attributes may be represented in some type of an information model. Vocabularies are mapped to standard terminologies. Specialized terms. Vocabularies are mapped to standard terminologies. That's a little confusing. Let's see, they have some more down here. Name standards. Okay, so they have some examples I can use here. So let's go ahead and put some examples in here. So, oops. Of examples of examples. So we have SNOMED CT, clinical terminology, global scope enabling automation of reasoning and analytical approaches to process HR data. Oink. Universal standard for identifying health measurements, observations, and documents. ARC's norm. Drug terminology for the US that presents drugs from prescriber's point of view. Ingredient plus strength plus dose form. So this one's a clinical terminology. This one doesn't really, it's terrible. I wish they would do a universal standard. This is a drug terminology. More examples. ICD-10 is cause of death coding, cause of death coding, and death certificates in use in US since 1999. C10CM, classification of diseases and related health problems. HIPAA. Oh. Yeah, stands for problems named HIPAA standard. Just put right there. And HIPAA standard for morbidity in outpatients and other care settings. ICD-10 PCS. Classification of inpatient procedures and the standard inpatient procedures. Name standards. I think name standards means the ones that are like name standards. Wow, there's quite a few. Okay, so we're going to keep going on. CDT is achieve uniformity. This is like really small. Okay, so achieve uniformity, consistency, and specificity in documenting clinical treatment. Oh, I didn't know there was one specifically for dental stuff. That's interesting. CPT. I should probably like write the things down. So I'm gonna write code on dental procedures and nomenclature. CPT is current procedural terminology. Or come back and write these in. ICD-10 International Classification of Diseases and Related Health Problems, 10th revision. Diseases, medical modification, 10th revision. SB10 procedure coding system. Systematized nomenclature for terms. Is logical observation, identifiers, names, and codes. Okay, good here. CPT is terminology used to review uniformly and consistently for ambulatory and hospital patient medical procedures and services by other healthcare professionals. HC expects level 2. Healthcare Common Procedure Coding System. National codes used to identify products, supplies, and services. Ambulance and medical equipment is used outside a physician's office. Oh geez, there's so many. DSM, sharing regulatory by humans. I think we'll keep these for now, or finish off with the NDC, just the name standards. NDC. National Drug Codes, Universal Product Identifier, Drugs Intended for Human Use Code, D Notes, Labeler, Product and Packaging. Cool. I think we're good with this. Oh damn, I already am far along. Yeah, we're gonna move on. That was good. So let's go ahead and take a look at data, taxonomies, and ontologies. Let's see. There's anything else? Taxonomy. This looks like an interesting read. Ontology and taxonomy. Stop comparing things that are incomparable. To many people, the word ontology might sound abstract. It has its origin in Tim Berners-Lee's dream of inventing the World Wide Web. This dream included the web becoming capable of defining a so-called semantic web by analyzing all web data, including content, links, and computer person and transaction. In the semantic web, the Resource Description Framework, RDF, and Web Ontology Language, OWL, have been established as standard formats for sharing and integrating both data and knowledge, the latter in the form of rich conceptual schemes called ontologies. In this article, the word ontology serves as the working definition. However, it is worth mentioning that in today's IT world, there is also a broad use the term knowledge graph to refer to this concept. Why to care about ontology? With regard to artificial intelligence, the terms big data, machine learning, and deep learning are solely replacing the usage of AI. However, to quote Adrian Bowles, there is no machine intelligence without knowledge representation. In other words, AI requires some elements of knowledge engineering, information architecture, and a significant amount of human work to do its magical neural network. Fittingly, Alexander Wisner-Groff finds that perhaps most importantly, we need to recognize that it is intelligent data sets, not algorithms, that are likely to be the key limiting factor in the development of human-level artificial intelligence. An ontology is a structured and formal representation of relative knowledge in a certain domain. Oh, I love that definition. This gives me goosebumps. This is how you know you're a nerd. This is necessary because, unlike humans, it cannot directly rely on human background knowledge about a term's correct usage. What an ontology can do, however, is to learn about the semantic meaning of a term through the interlinks between the concepts in its system. Let me read that one more time. This is necessary because, unlike humans, it cannot directly rely on human background knowledge about a term's correct usage. What an ontology can do, however, is to learn about the semantic meaning of a term through the interlinks between the concepts of a system. Powerful ontologies already exist in specific domains. Examples include the financial industry's business ontology, as well as numerous ontologies for healthcare, geography, or occupations. Another important part of AI is semantic reasoning. In addition to identifying potentially fraudulent transactions, determining users' intent based on their browser history, and making product recommendations, AI can also do the following. It can execute tasks that require explicit reasoning based on the general and domain-specific knowledge, such as understanding news articles, preparing food, or buying a car. Thus, such tasks require information that is not part of the input data, but needs to be dynamically combined with knowledge. This type of machine reasoning can only be achieved with ontologies and the way their knowledge is modeled. Taxonomy and ontology are fundamentally different. Ontology is often confused with taxonomy. Apart from the fact that both belong to the fields of AI, the semantic web and system engineering, there is really not much that would characterize them as synonyms. Taxonomy classifications such as ONET, Occupation Information Network, and ESCO, European Skills, Competencies, Qualifications, Occupations, simply cannot be compared to ontologies. They provide a much simpler approach to classifying objects, as they have a hierarchical structure and utilize only parent-child relationships without any additional, more sophisticated links. Ontologies, on the other hand, are a much more complex form of categorization. Speaking metaphorically, a taxonomy equals a tree, whereas a ontology comes closer to a forest. For example, the term golf could appear in several taxonomies. It might be located under a human activities tree, human activities, leisure activities, sports, and golf. It could also appear under a taxonomy concerning apparel, casual active apparel, sporting apparel, golf clothing, and accessories. It could even appear in something quite different. For example, an automobile taxonomy. Automobile, Germany, Volkswagen, golf. Each of these taxonomies can be considered a tree whose branches touch at their golf-related nodes. Put differently, taxonomies represent a collection of topics with is-a relationships, while ontologies allow for much more complex connections, such as has-a and use-a relations. Hence, if we return to the classification example above, taxonomies lack the capability to compare child concepts. In the classification of ESCO, almost all medical specialists are grouped under the heading Specialist Medical Practitioners. Furthermore, specialist skill sets are simply grouped in lists without any links to the respective specialist occupations. Why is that? One reason is that classifications are mainly used for statistical purposes. From this viewpoint, there is no need to further classify all individual medical specialists according to the skill sets and training background. Therefore, according to taxonomies, specializations can only be recognized by their job title, and one needs to refer to other sources to better understand their individual meaning. Building an ontology of occupations, qualifications, and skills make it possible to automatically recognize similarities and differences between job titles. For example, pediatricians and neonatologists have similar jobs, both of which concern themselves with the medical care of newborn infants. Where is it? Newborn infants. With the ontology modeling approach, it is possible to determine that a pediatrician has a very high percentage of similar skills to that of a neonatologist. However, pediatricians can only take over the neonatologist's job after further training. All this information can be represented in an ontology through the interrelations between concepts. This goes beyond the capacity of a simple taxonomy. Whoever wrote this is like super awesome at explaining things. Let me try to process this ontology here. They talk about pediatrician and a neonatologist. So pediatricians has a skill sets of pediatricians, skill sets of pediatric surgeon, neonatologist, surgeon, specialist medical practitioners. Oncologists, chemotherapist, surgeon. Ontologies enable matching data sets. When it comes to matching, say the matching of CVs with vacancies, there is no better way than to use an ontology. All too often, simple keyword-based matching or fuzzy machine learning methods are used for this, which means that many similarities go undetected and cannot be matched, such as keyword variations, synonyms, and alternative phrases. When matching, it is important to compare the semantics, the underlying meaning of two items rather than the wording. This is where the ontologies come into play. They can provide a semantic modeling that can detect the underlying meanings and similarities in CVs and jobs descriptions. The ontology matching technique represents a fundamental technique in many areas such as ontology merging. In domains with very complex rules and complex interactions between rules, there's no substitute for ontologies. This is shown, for instance, when you consider integrating disparate domains. Let's say there are two separate ontologies, a weather ontology and a geographic ontology. I'm considering navigation or insurance risks to create a third ontology which integrates and leverages the other two as a manageable proposition. The true value of ontologies. The semantic system relies on explicit, human understandable representations of concepts, relationships, and rules to develop the desired domain knowledge. It is impossible to rely solely on programmers to build such a system based on machine learning, as they lack the knowledge needed to define relationships between concepts in the specific domains. Therefore, the domain knowledge must be learned from domain experts with various backgrounds: intellectual property law, fluid dynamics, car repair, open heart surgery, or education and vocational systems. This process is crucial for creating a comprehensive knowledge representation. For the multilingual JN's ontology, language skills are a key point. In many cases, a one-to-one translation of a concept into multiple languages is impossible. However, thanks to Switzerland being small and integrated, all the JN's ontology curators are fluent in at least 2 languages, and some speak even more than 4. This advantage guarantees the ontology's consistency and quality across different languages. Oh, this is so fantastic. I think anyone in informatics, would love these kind of topics. This is so awesome. Oops, that's not what I want to do. Go back to here. I'm going to use this as the definition, even though it a great explanation between difference of ontology versus taxonomy. Let's go ahead and cite this in there. Whew. Link this, and then maybe I'll copy like one of the examples because this was a really great read. Okay. Come on. All right. I think this is like all we need here. Paste without formatting. Yeah, that's the same one. Okay. All right, I think this is, maybe we'll take a look at one more. There's a healthcare example one. B, right? Yeah. Let's take a look to see. Data, yeah. Healthcare engineering. Let's see. Taxonomy-based approaches to quality assurances of ontologies. Ontologies are important components of health information systems. As such, the quality of their content is of paramount importance. It has been proven to be practical to develop quality assurance methodologies based on automated identification of sets of concepts expected to have higher likelihoods of errors. Four kinds of such sets, called QA sets, organized around the themes of complex and uncommonly modeled concepts, are introduced. A survey of different methodologies based on these QA sets and the results of applying them to various ontologies are presented. Overall, following these approaches leads to higher QA. It'd be nice to have something more. The role of taxonomies. When most people think of artificial intelligence, they conjure up notions of advanced machine learning algorithms, deep neural networks, or computational cybernetics. You know, the sexy, futuristic sounding concepts that are having an impact on the world around us. What doesn't come to mind are taxonomies, ontologies, and schemas. Not as sexy. I disagree. But equally, if not more important in the role of bringing AI to life. AI and machine learning requires structured information to train machines to learn and understand how to replicate human behavior. The process of creating structured information from unstructured data and using it to teach machines to think like humans starts with the creation of clean structured data for AI and ML processes. Taxonomies provide the means for machines to understand hierarchies in the information. Ontologies specify the domains. Schema gives clarity of how data is structured. Before we proceed, let's break down what each term really means. What is a taxonomy? A data taxonomy is the classification of data into categories and subcategories. It provides a unified view of the data in a system and introduces common terminologies and semantics across multiple systems. Taxonomies represent the formal structure of classes or types of objects within a domain. A taxonomy is static. An ontology is a formal naming convention and the definition of the types, properties, and interrelationships of the entities that really or fundamentally exist for a particular domain of discourse. An ontology is dynamic and domain-centric. What is a schema? In computer programming, a schema is the organization or structure for a database. A schema is a formal expression of an inference rule for artificial intelligence computing. What is a knowledge graph? A knowledge graph is a model of a knowledge domain created by subject matter experts with the help of intelligent machine learning algorithms. It provides a structure and common interface for all of your data and enables the creation of smart multilateral relations throughout your databases. Structured as an additional virtual data layer, the knowledge graph lies on top of existing databases or data links to link all of your data together at scale, be it structured or unstructured. Leveraging the learnings, information can be structured to create meaningful representations through automation. This becomes the basis for machines to understand the information like humans, recognize patterns, and predict relationships. When this intelligence is combined with tools like knowledge graphs, machines can read and predict the connections, interrelations, and interpret the data. Knowledge graphs provide the interface to leverage the learning and visualize the relations over large data sets of information, enables humans to make sense of large unconnected databases based on the predictions from machines to take data-driven decisions. When the humans check the predictions and correct anomalies in the predictions from machines, the supervised learning cycle kicks in, improving the intelligence, driving higher accuracy of predictions. These technologies are extensively used for AI and ML-enabled recommendation engines, fraud detection, anti-terrorism, risk management, and much more. The key difference between ontology and taxonomy is an ontology is a subset of a taxonomy. A taxonomy formalizes the hierarchical relationships among concepts and specifies the term to be used to refer to each. It prescribes structure and terminology. An ontology identifies and distinguishes concepts and their relationships based on a domain. It describes content and relationships in the context of a specific domain. For example, let's say a taxonomy has been created for contracts management. It will contain the terms and relations for contract documents. If this taxonomy is applied for information extraction from OTC or over-the-counter derivative contracts such as ISDA, GIMRA, the taxonomy alone would prove to be inadequate, as industry-specific contracts like ISDA, GIMRA have their own domain-specific ontologies. Similarly, contracts for rights management, supplier contracts, each has an ontology which is domain-specific, provides the best reference of terms applicable in that domain. Therefore, the right choice of taxonomies and ontologies is crucial for AI and ML applications to work successfully for information extraction. While slightly different, they are all related to metadata, information organization, knowledge representation, although each one has a specific role to play in representing information. I think this is like another great one to cite. Just copy and paste this whole thing. This is the role of taxonomy and ontology. I think I can read about this all day. I think I kind of miss reading about all this stuff too. Okay. I think I cited this already. I think we're gonna end it here. Got a little too excited reading about this. Go ahead and end the live stream here. It's already pretty late. This was a fun night though. Okay, let's go ahead and link. All right, I think that's it. We'll call it a day for this, and we'll kind of end it here. Thanks for everyone that has tuned in. See you guys tomorrow. Bye.